Howdy and welcome to Math 153 Elementary Statistics. I'm Lance Curtis and this is the lecture for section 1.1 and 1.2. In this first chapter, we're going to be providing a basic foundation for statistics. And the first section, we're just going to review some main ideas that we want to get out of the first chapter. In the second chapter, we're actually going to delve into the first of those, which is critical thinking. You can see an overview of the first chapter here. So let's get started with the first section. There's some basic vocabulary that we need to understand in this beginning of statistics. And the first thing that we need to understand is what statistics is. Essentially, statistics is about collecting and analyzing data and then taking that analysis and interpreting it to make conclusions about the data set. So we're looking to make predictions about what might happen in the future. We're looking to establish a trend. Maybe we're looking to establish a relationship or a connection between two or more variables. So statistics is the science of getting from the beginning of collecting all that data and then ending up with your final conclusions. The data is simply collections of observations. So it's whatever we're measuring, different categories in our data set that reflect the subjects that are under study. And speaking of the subjects that are under study, we have to understand differences in terminology. So if we want to look at the complete collection of everything, then that's going to be our population. If we wanted to make a study to characterize the population, one approach is to take a census, okay, which means we're collecting data from every member of the population. For most applications, that's typically not done because trying to get responses from every member of the population is not only next to impossible, but it's also very time-consuming and very costly in terms of money. So in order to preserve resources, what you want to do is take just a portion of the population, which is what we call a sample. Now, how you take the sample and what sample you actually take are going to play a large role in the validity of the conclusions that you draw from your study. We'll definitely be talking more about that later in the course. But for right now, what you really need to understand is the difference between population and sample. Here's a good example. Let's say the Gallup Corporation collects data from a survey about identity theft. And they basically asked 1,013 adults, are you worried about identity theft? And 66% of the adults responded, yes, we are worried about it. Okay. Well, in this case, the entire country is the population, all 241 million people living in the United States. That's the population. That's everything. Okay. But we're not going to ask all 241 million. We only asked 1,013. So this 1,013 is the sample for our statistical study. Okay. Our objective is to use the sample as a basis for drawing conclusions about the whole population. This is why we take a sample. Okay. It's much easier to get answers from 1,013 people than it is from over 241 million. So we're going to use the sample to characterize the population. And this is one of the main thrusts of statistics. To take characteristics from that sample and to then draw from that characteristics of the population as a whole. That's the main idea that we're going to touch on in chapter 1. Okay. Now, let's dig into the next section, section 2, where we talk about critical thinking. Critical thinking is one of those skills that all educated people need in today's modern society. And in fact, with the proliferance of the internet and social media, where people are having more and more discussions that are absent of critical thinking, well, the study of statistics can help us to develop those critical thinking skills. So let's dive in. Key concepts from this section. Okay, we're basically going to look at an overview of the process of conducting a statistical study. And there's three main steps that we run through: prepare, analyze, and conclude. Let's look at each of these steps in turn. First, prepare. We want to take good steps, good measures to make sure that the data that's coming into our study is good data. Okay? The old adage of garbage in, garbage out definitely applies here. Okay? You put garbage in, you're going to get garbage out. It's really hard to get valid conclusions when your data set is not up to par. So you have to consider the context of the data. What did the data really mean? Where did the data come from? And what's the intention of the study? What is it we're trying to do? We're trying to establish a relationship. We're trying to make a prediction about the future. What is it that we're trying to do? So this context is really important. We have to get that straightened out before we even start the study. Okay, then we have to look at, where's our data going to come from? If there's a strong bias in the data, then that's going to affect the validity of the results. Okay, so for example, let's say that a candy company supports and finances a statistical study about chocolate, and the study concludes that chocolate is good for your health. Well, chocolate may or may not be good for your health, but the fact that, the person or organization that was sponsoring the study has a financial vested interest in the study making a certain conclusion, well, we might want to take a look at, where's your data coming from? Because if you cherry pick the data, that's going to affect the results you get out of your study. We'll talk about that more in a future lecture. And then, of course, sampling method. I hinted at this previously, but it's really important to look at how are you getting your data. Okay, not only where it comes from, but how you're collecting it. Does your sampling method influence the validity of your conclusion? Well, it might. If you're taking a survey, but you're only taking surveys from people who volunteer to participate in the survey, well, those often have bias. Okay, since those with a special interest in participation are more likely to participate. There are other ways to get better results, and we'll talk about some of those sampling methods again in a future lecture. Once we've prepared our study, then we need to analyze. So we've got our data, we've collected it. One of the first things you need to do with any data set in order to get a good understanding of it, put your arms around it, is to make the appropriate visual representations. Oftentimes, the right visual representation will tell you everything you need to know about your data set. You don't need to go and make tons of charts and graphs. Typically, making just the right graph is enough. And the more experience you get with this, the more skilled you get at figuring out, okay, this is the data set, this is the data set, this is where it came from, this is the purpose of the study, this is the type of graph I need to make. It just comes with experience. And we'll cover a lot of this in more detail in the next chapter. Once we've got an understanding of our data set, then the next step is usually to apply a series of statistical methods. Now, you're fortunate to live in the 21st century because, when I went to college, back at the end of the 20th century, a lot of old school approach was emphasized. And so the equations that are used in statistics, mathematical equations to get our results, are really burdensome, and they're a real bear to work with. I will show you the equations. I'm not going to make anyone use them, okay? In fact, when you see these, most of you are going to look at this and say, oh my goodness, what have I gotten myself into? But rest assured, okay, you're going to enjoy the benefits of living in the 21st century because here we have computer software that does most of this number crunching for us. We still need to apply some good judgment to what the software is going to be telling us. So there's still a human element involved that requires an understanding of the statistics that's used to code the software. But, a lot of the number crunching is going to be done for you. Okay, that takes a lot of the unpleasantness out of statistics itself. We'll also get into that further into the course. Once we've done our statistical analysis, then we're ready to make conclusions from the study. And typically what we look for when we're making conclusions are relationships between variables that have what we call statistical significance. Okay? A statistically significant result is one which is very likely to occur by random chance or circumstance. So this is very important. This is why we look for statistical significance, because what it says is that, well, this relationship that we see in our data set is not circumstantial, or is extremely unlikely to be circumstantial, would be a more accurate way to say it. We always want to look for statistical significance, and sometimes a study will show you that there's no statistical significance between your variables, in which case it's like, well, it's more likely that any relationship that we do find is going to be circumstantial. You don't want to be making the case that one thing causes another when all of your evidence is circumstantial. So you really want to understand this concept of statistical significance. And then, of course, many of the people that are looking for the conclusions from your study are not going to be well-versed in statistics. So we want to state the conclusions of our studies in ways that lay people, quote unquote, can understand. We'll also get into these concepts more as we get into the course. Now, here's an example of what I'm talking about when I say statistical significance. Okay? Let's say we have a test of the Atkins weight loss program. So we're going to survey 40 subjects, and over the course of 1 year, these subjects were on the Atkins weight loss program, and they lost an average of 4.6 pounds. So just under 5 pounds in 1 year. Now, running our statistical study, we find that there is statistical significance with a weight loss of 4.6 pounds in 1 year. But seriously, I mean, is that practically significant? I mean, how many of you are going to fork over money, good hard cash, for losing just under 5 pounds in the space of 1 year? I know I'm not going to. And so you can see there's a difference here between statistically significant and practically significant. And that's why we have the software that spits out the numbers, but it takes common sense and good judgment to make sense of what that result is and whether or not it's really something that's worth paying attention to. To wrap up our lecture here, I want to finish up looking at some potential pitfalls. Okay? There are a lot of pitfalls that people who conduct statistical studies make. One of the biggest pitfalls that people using statistics make is in the area of misleading conclusions. And I cannot overemphasize this enough. Okay? They're looking at two different variables, and the statistics tells them that they have high correlation. Okay? There's statistical significance between the two variables. Okay? But correlation does not imply causality. In other words, just because two variables are highly correlated, it doesn't mean there's an association or a relationship between the variables. It doesn't mean that one variable causes the other. Okay? For example, let's say we did a study of people who smoked, and we're looking at relationship between smoking and pulse rate. Well, if you get a high correlation value between those two variables, you might erroneously conclude that one of them causes the other. But really, when you think about it, the influence of smoking on pulse rate is no different than the influence of any sort of activity that requires the same amount of physical exertion as smoking. So there's really no relationship between the two, but there is correlation. So the one is not the same as the other. The classical example of this concept is, if you look at the graph there towards the bottom right of the slide, you can see data plotted for two variables. So on your x-axis on the bottom, you're going to have elementary school, you're going to have the number of bars in town. And on the y-axis, you're going to have elementary school teachers. So looking at the data, we can see there's a line of best fit running through the graph, and the closeness of the data points to that line of best fit is really what correlation is measuring. So what we want to do is get a value of correlation that's high, which means that the distance on average of the data points from that line of best fit is really small. We want them to be closely fit, aligned with the line of best fit. Well, looking at this data set, it's very clear that we have good correlation because those data points are very close to that line of best fit. But just because the variables are highly correlated doesn't mean the one causes the other. I mean, what does the number of bars have to do with elementary school teachers? I mean, if we run with that conclusion from the statistics, we'll be saying that if you want more school teachers in town, just open up more bars. What sense does that make? That's ridiculous. Okay? What we're really looking at here are two variables that are symptomatic of the same third variable that's not in the study as directly as these two variables are. And that variable is the growth of the community. You know, when a community grows, it's going to need more services because there are more people requiring services, hence the increase in the number of bars. But more people also means more families means more children means you need more school teachers. So what we're looking at here are not two variables where one is causing the other. We're looking at two variables that are highly correlated because they're both caused by the same third variable that's not directly accounted for in the study. Again, correlation does not imply causality. They may be correlated, but that doesn't mean there's a relationship between the two, or at least not a direct one. Another pitfall that many people with statistics fall into is taking sample sizes that are way too small. Okay? So, for example, let's say you're going to use statistics to figure out what the suspension rate of a school would or should be. And so we're going to take a sample size of 3 students. Now, I don't know about the size of your high school. My high school was a lot bigger than just 3 students. I mean, 3 was really, really small number of students who were actually attending the high school. Now, maybe you went to a high school that had 5 students in it. And if your total population is 5, then a sample size of 3 is more than likely appropriate. But I'm guessing that's not most of you. Most of you went to high school at somewhere, where the numbers were much larger. So you want to make sure that your sample size is sufficiently large. There are mathematical equations that we can use to tell us that information. And many of these are programmed into the software packages that you can use to run statistical studies. So it's really easy to get a sufficient sample size, to know what a sufficient sample size would be. Actually, getting that sample size may be a different question. But it's really easy to let the math tell you, okay, what the sample size should be. And that's what you should do. Let the math tell you. Missing data is another pitfall that many statistics users fall into. They try to make a model with a data set that's missing a certain proportion of the population. And you can run into a large number of issues with that because the sample size that you take needs to be representative of the population. And the more unrepresentative the sample is of your population, then that's just going to make the conclusions you draw from your study all the more unreliable. Another point in connection with missing data is the idea that you can make a model that tells you anything you want to hear. And I saw this all the time working in industry, where people who had a vested interest in a model that had a certain favorable conclusion, when they learned that it could be produced by taking out a certain data point or leaving a certain one in, then they were in those meetings where we were discussing the data, and I kid you not, I mean, they were so hardcore on their agenda to either take the data point out or leave it in. Just one data point. Okay. Now, depending on the size of your sample, okay, leaving one data point in or taking one out can make a big difference, especially where it is with respect to the other data points. Missing data can dramatically affect your results. Okay, so if you want a model that tells you something, you just got to massage the data the right way. Okay, another way to massage the model is to use the data, but to change the boundary conditions. So let's say, for example, I'm making a model that predicts failure in a given part. And let's just say the part is a combustion can in a gas turbine unit that produces electric power. Okay, so a crack in a combustion can can be varying lengths. So we're going to define failure as any crack that's longer than 1 inch. So we take our data set, and all the data points that represent cracks greater than 1 inch are going to go into our model. That model is going to give us a certain result. Well, if we go back and say, okay, wait a minute, we're going to change the boundary conditions. We're going to adjust our definition of failure to be something completely different. Okay, let's say, okay, now we're going to say failure is any crack greater than 1/2 inch. Well, presumably that would increase the data in your model, but it would also give you a very different result as far as predicting when a combustion can is going to fail. So the way you set up the boundary conditions, how you define things at the beginning to decide what's going to be included and what isn't going to be included, makes a big difference as to what the model that you're going to make is going to tell you in the end. And then, of course, sometimes, and this is very true in the world of surveys, and especially the U.S. Census is infamous for this, sometimes you don't get all the people that you want to get in your data set. Okay? I say the U.S. Census is infamous for this because not everyone that should be included in the census is included in the census. One of the most underrepresented groups in the census are people who don't have a home or people who have low income. I mean, do you really want to be marked forever in history for historians forever and a day from now to look at and see your name under the title of impoverished or homeless? I mean, most people don't want that. And so these people generally opt out of these types of activities, and therefore the result is something that's somewhat underrepresented what it should be. So missing data can be a huge problem, Another problem, especially when you're talking about surveys, is the idea of loaded questions. Many people think that a survey is just something you just throw questions together, as many questions as you want, and you'll find that you can get whatever data you want from people. But the reality is something very, very different. Okay? How you word the question makes a big difference to the results that you get. There's an example here on the slide. If I were to ask, should the president have the line item veto to eliminate waste, then we can see here 97% of people respond to that with a yes in the affirmative. But notice how the number of affirmative responses go down if I change the wording of the question to, should the president have the line item veto or not? See, in the first instance, the question is worded in such a way as to suggest that there's one option that's approved. Whereas the second wording, the second option provides the participants with a choice, okay, and the participant can choose one or the other. So the number of affirmative responses go down when people have a choice. So how you word the question can make a really big difference as to the results you get from a survey. The order of questions is also important in a survey. I mean, for example, if I were to ask the question, would you say traffic contributes more or less to air pollution than industry? You can see the results here on the screen. 45% say traffic, 27% say industry. But if I reverse the order of the items in the question and ask instead, would you say industry contributes more or less to air pollution than traffic? You can see how the numbers change here on the screen. So looking at this, 27%, 24%, those are around the same ballpark for industry. So I wouldn't say that that's substantially changed. But at your bottom dollar, there's a significant difference between 45% and 57%. So how you order the questions makes a big difference into the results that you get. And then, of course, there are people that just don't respond to surveys, okay? And this can introduce a certain amount of bias in your results because people who won't participate in a poll have a very different view of the world than those who would welcome the opportunity. It's just been scientifically proven that that's true. And so if you get a lot of non-response in your survey, in your data collection, then that's going to influence the validity of the results that you get. So you want to make sure that you employ methods to reduce as much as possible the amount of non-response in your survey. Another pitfall that many people related to statistics fall into is mistaking the difference between accuracy and precision. Many people believe that accuracy and precision are synonyms. They mean the same thing. But these two terms are actually two very different animals. Precision refers to how close measurements are together. So if you look at the target on the far left, you can see that all of the shots are really close together on the target. That is precision. Okay. However, they're also very far removed from the center. Okay. Therefore, they're not accurate. Accuracy refers to how close measurements are to a given standard. In the case of a shooting target, you're looking at the center of the target. That's the standard. So that first target there on the far left, these shots that we see are precise but not accurate. You're going to the next one, just to the right of it. The shots are all kind of sort of somewhat around the center, so they are accurate because they're close to that standard, but they're not very close to one another, and so they do not have precision. Looking at the next target, we see neither precision nor accuracy. The shots in that third target are really separated both from each other and also from the center, which is the standard. So no precision, no accuracy. The last target, the one on the far right, we have both precision and accuracy. All of the shots are close together. That's precision. All the shots are close to the center, which is the standard. That's accuracy. So it's really important to understand the difference between precision and accuracy, because just because a number is accurate doesn't mean it's precise. And just because a number is precise doesn't mean it's accurate. Two very different concepts. And then there's also the pitfall of percentages. Now, percentages abound in the statistics. And many people, most markedly in the media, like to take percentages that they hear and run with them. This is also common in the world of advertising and politics. They take percentages and they use these percentages, and while there is some fact in which the percentage is based, the way the percentage is being used can be very misleading or confusing. For example, there was once an ad that was run by Continental Airlines about lost baggage, and in the ad they claimed, "We've already improved 100% in the last 6 months." Well, what exactly does that mean? 100% of what? It's presumed that you're talking about lost baggage because the statement is being made in the context of an advertisement talking about lost baggage. But, we've improved 100%. You want to improve lost baggage. Okay, the positive in this case is going to be a decrease. And when you look at, an improvement that's a decrease, you can't improve more than 100% because 100% takes you to 0. So then, are we saying here that Continental Airlines made no mistakes? I mean, to improve 100% means you got everything down to 0. Does that mean you're making no mistakes? I mean, it's just misleading conclusions. It's not clear what exactly they're talking about because they're obfuscating some of the facts in which this percentage of 100% is being based on. So you really got to be careful when you're talking about percentages because they can be used to mislead and confuse. And that brings us to the end of this lecture. If you have any questions, be sure to find me. You can find me in class, office hours. You can also email me. You can make an appointment with me if the office hours don't work for you. Just make sure that you get your questions answered. And if you have no questions, then I guess I will see you in class.